This video is going to be to introduce you to the vocabulary associated with nuclear reactions. First term we're going to learn is unified atomic mass, which we represent with the letter U. The unified atomic mass is 1/12 of the rest mass of an unbound atom of carbon-12 in its nuclear and electronic ground state. Because carbon-12 has 6 protons and 6 neutrons, when I divide that mass by 12, I get the approximate mass of a proton or a neutron, which is 1.667 times 10 to the minus 27 kilograms. The next term you need to learn about is binding energy. This term's kind of a misnomer because it sounds like it's the energy of something bound together, but actually it's the work or energy required to completely separate all of the nucleons of that nucleus. Lastly, we have mass defect, the difference between the mass of the combined atoms and the sum of the combined atom and the sum of the mass of the constituent parts. So this sounds a bit new, and so this is going to blow your minds, but the total mass of all the protons and neutrons, all the nucleons that go into a nucleus, is actually greater than the mass of the nucleus once it's combined. So where does that extra mass go? Well, energy and mass are equivalents according to E equals mc squared, where E is energy, m is mass, and c is the speed of light. And so when the nucleons combine, they go to a lower energy state, and so the final nucleus releases that extra energy in the form of kinetic energy. All right, so those are all the terms you need to know. Now let's talk about the concept of binding energy per nucleon. So remember, binding energy is how hard it is to pull our nucleons apart in the nucleus. So if I wanted to find the binding energy per nucleon, or the average binding energy per nucleon, I would take the total binding energy and I would divide it by the number of nucleons that I see in that nucleus. For example, carbon has 12 nucleons, so I would divide by 12. This number is important because the greater the binding energy per nucleon, the more stable our nucleus is, right? So the higher the number, the harder it is to pull apart that nucleus, meaning it's more stable. You'll see at the peak of this binding energy per nucleon graph is the element iron 56. So iron is the most stable, iron 56 is the most stable isotope, so it's at the peak. So it's the hardest to pull apart once we've put it together. So as I go from 0 nucleons to iron, I become more stable. So I increase my binding energy per nucleon. So as I add more nucleons to my nucleus, I increase the stability until I get to iron. However, once I get to iron, my binding energy per nucleon decreases, meaning I'm becoming less stable as I add nucleons. So this is why nuclei like uranium want to break down into smaller nuclei. And so in order to become more stable, smaller elements, as they approach iron, do fusion, where they combine smaller nuclei into larger nuclei. So this half of the curve favors fusion. And on the right-hand side of iron, this half of the curve favors fission. So they want to break down to smaller nuclei to be the size of iron. All right, that's the end. You'll learn about fission and fusion more in the next video.